Alright, now that we've covered graphing basics, let's actually discuss what these graphs mean and how to get something meaningful out of graphs. Ultimately, graphs tell you relationships, or rather, how the color, the independent variable on the x, affects the period on the y-axis. Or rather, how does x affect y, which comes down to a proportionality. Y is proportional to, how is y proportional to x? And that's why I gave you guys 5 basic proportionalities that if you remember those, you should be good to go for anything. And I'll pull those up right now. So these are the 5 graphs that you should be familiar with. If you see these 5 graphs, you're ready to rock and roll. Or rather, if you can remember these 5 graphs, you're ready to rock and roll. The first one is no effect. So let's say we're going to use that same example I was discussing before. These are all different graphs of period as a result of color. Or rather, color was my independent variable and the period of the pendulum was the resulting dependent variable, excuse me. In the first one, we get no effect. And that's if you get a completely straight line across. That's no effect. That means if you look at the equation for period of a pendulum, color should not appear in it. Or rather, period is not proportional to color. I'm going to look at this third one next because I think that's the next one that's extremely straightforward and extremely easy. If you get a linear line like this, then they are directly proportional, or rather, the equation for it is going to be some other variables, and you're going to have to test multiple variables to find what those other ones are, affect the period, but also the color affects the period. So this is ultimately going to be how we determine the equation for the period of a pendulum, or anything that you want to see. How is this affected by this? Learning these 5 graphs, 1, 2, 3, 4, 5. If you can memorize those 5 graphs, you can learn any relationship. And one is easy, it doesn't appear in the equation. The third one is they're both in the numerator, or both in the denominator, but they're both in the same position. They're both on the top or both on the bottom, but period is equal to some other variables or some other constants times color. So those two are easy. Now, if it's not a linear relationship, then we're going to have to look a little more closely at these other 3. And squared is a little bit too basic. I think exponential would be a better fit. And I will try to go back and change the rubric for this so it includes that. And the same for square root. It is a root proportionality, not necessarily square root, just like this is an exponential proportionality, not necessarily a squared proportionality. And I will go more in depth with those back in the graph section. But ultimately, these are the 5 graphs you're going to be paying attention to, and if you can remember those 5, you're set. So no effect, directly, inversely, and inverse means it's going to be in the denominator somewhere. Root proportionality means the period is going to be affected by either the square root, cubed root, fourth root of color, and exponential is going to be proportional to color to some exponent, whether it's color squared, color cubed, color to the 4th. But now it's time to actually show you guys how you figure out that relationship. So your ultimate goal is if you get a linear graph, you're great. And that's what I showed you. No effect, directly proportional. Where no effect means it's not in the equation, and directly proportional means, hey, color is in the numerator of the right side of the equation. But if it's not linear, you're going to have to regraph it. So let's look at the first example. Let's look at exponential. Let's say you graph period versus color, and you get this curve up shape. If that's the case, then period could be proportional to color squared, it could be proportional to color cubed, color to any exponential graph. The way you figure out which one it is you have to go back into your data table and make a second data table of period versus color squared. And then once you fill that data out, you're going to have to regraph it and hope that you eventually end up with a linear relationship. And if you do with t versus c squared, hey, that's your relationship. Period is proportional to color squared. However, if you graph t versus color squared and you still get a curve, whoopsie daisy, excuse me, if you still get a curve, then that's not quite right. You're going to have to jump to t versus c cubed, which means you're going to have to make another data table and regraph until you get it linear. That's your ultimate thought, is number one, figure out which of these 5 relationships it is. And if it's straight, you're set. And if it's curved, regraph until you get it straight. So regraph until linear. That's the ultimate sentence that could, or 2 words that could summarize this entire thing is, or 3 words, regraph until linear. So because we did get this second relationship right here, that means period is proportional to color squared, or rather the equation would be t equals any other variables it's related to times c squared, or constants. Other variables are constants. And let's say you also tested mass and found that that was also directly proportional, then it would be equal to m times c squared, and that's c color, not c speed of light. So it's not E equals mc squared, but t equals mc squared. And I just want to clarify, I just made up mass. So if you're like, hey, where did that mass come from? I was just saying, if you did other graphs for mass, let's say you tested color first and you found t is proportional to c squared, and then you made a second graph for mass, t is directly proportional to mass, then it would be m times c squared, because t is proportional to m and t is proportional to c squared. And we're just going to repeat that process for the other 2 types of graphs. And then you guys are covered for nearly everything with graphs. All right, so let's now look at the root proportionality. You end up with this downward curve. That should be immediately recognizable. Hey, this is getting smaller and smaller and smaller, but still increasing a little bit as the color is increasing. So period is increasing, but less and less and less as color is increasing. That's indicative of some root proportionality, square root, cubed root. And just like I said, you're going to have to regraph until linear. So if this is the case, always start easy. I'm just going to do the square root proportionality first. And then I'm going to calculate the square root of color, put it in the second column, and leave my periods unmodified in the first column. And I'm going to graph period versus the square root of color. And wouldn't you know it, that gave me a straight line. So now I know that period is proportional to root color, or y is proportional to root x. So then my equation would be t equals some other constants and variables times the square root of x, because square root of x is what gave me a linear relationship. And this would obviously have some slope m, different than the mass I used in the previous example. I really wish I didn't use m, but I did. So then let's say you measure the slope of this to be equal to 6. Well, that would be 6 times the square root of color. And that 6 might be a result of other variables and other universal constants. You never know. Or at least you never know until you test all other variables that you can think of. So in this case, t would be equal to 6 root c. However, if you still get a square root proportionality, what are you going to do? Regraph until linear. So I'm going to do the next level root, t equals t versus the cubic root of color. And then calculate the cubic root of color in the second column, leave period unmodified, and regraph until linear. And in this case, hey, period was directly proportional to the cubic root, or t equals some other variables and constants times the cubic root of color. And I'm using color because I don't want to give anything away, and I also don't want my graphs to contradict your graphs. So I use something that we all know has, hopefully, no effect on the period of the pendulum. Changing the color of it, even though it may absorb more or less light, should not affect the period of a pendulum. All right, and your final one that I do want to discuss with you is inverse proportionality, or rather, it goes in the denominator because that's what an inverse is. And that's anytime you get this downward curve. So period is proportional to 1 over c. So if that's the case, what are we going to do if we get a curve? If you get a curve, regraph based on the type of curve. Where a curve up is exponential, curve down is a root, and a downward curve is an inverse proportionality. So I'm always going to start with the easiest one, 1 over c, and you're going to get vozha. Oh, your periods will remain unmodified. And in the second column, I'm going to do 1 over my first color, 1 over my second color, 1 over my third color. All of these should be switched because my independent variable should come first. I'm sorry. So this should be 1 over color versus period. But hopefully you guys get the idea from that. Is this working? That's working. Sorry about that. I think my previous video is finished, so I'm going to process that while I continue working on this. All right, sorry about that. So if you get inversely proportional, that means that our equation is going to have to be t is equal to 1 over c, or 1 over c squared, or 1 over c cubed, or maybe even 1 over root c. We don't know. But your standard policy is always regraph until linear. Regraph. So let's say you do 1 over c, and how that affects the period, or period versus 1 over color. If that comes out to be linear, congratulations. You have just proven that period is equal to some other variables and constants, which would be equal to your slope, times 1 over color. However, and that's ultimately how we build the equations in physics. That's where all equations essentially come from. All right. So now the what if? What if you graph 1 over c and you end up with this graph? You should think that through a little bit, and I'll hide the answer on the right side of the screen. That looks an awful lot like a root proportionality, which means my next thought is, oh my goodness, I need to graph. Well, we already determined that it was inversely proportional. So my next data table, again, regraph until linear, is going to be 1 over root c. So I'm going to calculate 1 over root c for all of my values and re-enter my periods for each color. So whatever your color was, 1 over root c, and I'm going to regraph this data. And hopefully that will give you, I didn't draw that. Hopefully that will give you a linear relationship 1 over root c. If it's not, you might end up with this. Whoopsie daisy. You might end up with this. You would have to try 1 over cubic root of c, or 1 over the 4th root of c. Keep revising until linear. And this is your slope. So now, once you've done all of this, and this is my final thought for the video, and my final thought for all of graphing, and this is a challenge question, which I'm just going to pose it to you. Let's say you graph t versus c squared, and you get this graph. Well, all graphs can be broken down into y equals mx plus b once you get them in a linear proportionality. So period is equal to whatever your slope is, and you would calculate that. So period is equal to the slope times, c squared, that's my x value, plus whatever your slope-intercept is. And you can look right at the graph and say, oh, that's coming across at the 3.1 second mark. C squared plus 3.1. And that would be the equation for the period of a pendulum if this was the slope, if this relationship was right, and if this was the initial period given by your graph. Or rather, this is the initial period, which makes no sense in this situation, right? Because we're not starting with an initial period. If there's no color, there's no period because there is no object, which is a weird thought. Now, the final graph I haven't discussed, and this can apply to any of your linear graphs, but let's say you get a downward graph, a downward graph. Well, that's just a negative relationship. So let's say you graph t versus c squared, and you get this negative graph. You would see it in the first graph, but regraph until upward and linear. So because it's negative, I would regraph, and I'll erase this. If it's negative, you would regraph t versus negative c squared. Again, always have to make a new data table, negative c squared versus period. Fill in your data, and hey, wouldn't you know it, we get a linear relationship. In fact, let's make this even more involved. Let's give it a slope-intercept, or a y-intercept. You get, well, all linear graphs can be broken down into y equals mx plus b. So, period is equal to slope times negative c squared, and really we can bring that negative out to the front, plus whatever this y-intercept is, which I'm just going to leave as b. That is everything I can possibly think about for graphs that doesn't involve SOHCAHTOA, which we will do later, but for now, these are all advanced graphing techniques that you could possibly need to determine nearly every physics relationship, every physics equation. I hope this video was helpful. I hope you got something out of it. And if you made it to the end, let's pop in another dad joke. Why don't pirates take baths when they walk the plank? Because they just wash up on shore. If you made it through this whole video, thanks for watching, everybody. I hope you have a great night. Bye.